we're going to take a look at one of the more prominent functions in MATLAB with respect to differential equations, the ODE 45. And ODE 45 is essentially going to give us the numerical solution, much like one of the numerical methods would, like Euler's method or the Runge-Kutta method, etc., to be able to solve our differential equations numerically. All right. So one of the things that we like to do is see how accurate the ODE 45 function is when we're trying to solve these sorts of differentials that are solvable using analytical methods. So we're going to take a look at the ODE 45 function, and we're actually going to have to create two separate sorts of files to do this. All right. So there's a little bit of technical stuff, not too much with respect to MATLAB, but we are going to create a function, and it's going to be a fairly easy one. And it's going to be a separate file, and then we're going to do the body of the executions in another sort of file. So let's take a look at how we can kind of tie the ODE function in with some of the things that we've already done in the course. So let's say we have a differential y prime equals 2x minus 3y, and the initial condition is y at 0 equals 2. We're going to find the analytic solution, and then we're going to find the analytic solution at 0.5. We're going to approximate that. We're going to find the ODE solution, and we're going to find that with step size 0.05. Then we're going to go ahead and compute the percent error between the analytic and ODE 45 solution. We're going to plot both the analytic and the ODE 45 solutions to kind of see if they match one another. And then based on everything that we get from all the parts preceding, we're going to make some sort of conclusive conjecture about how good ODE 45 is with respect to the analytic function. All right, so I'm going to start a new script, and we're just going to start by finding the analytic solution. So I'm going to clear all, and I'm going to CLC. I'm going to have some sims variables. So I'm going to have sims x and f or y at x. And let's have our analytic solution to the differential equation y prime equals 2x minus 3y. So we're going to desolve, and I'm going to call this analytic S. So analytic solution. I'll just call it analytic sol. That's going to be dsol, and we're going to say diff y comma x is going to be equal to 2 times x minus 3 times y. And the initial condition was that y at 0 is equal to 2. So we're going to have y at 0 double equals 2. All right, and that's going to be our analytic solution to this. All right, so let's go ahead and run that. I'm going to have to save my file. It might take a moment just because I haven't run this yet. Shouldn't take too long though. And while we're doing that, I'll go ahead and start part B, where we have to approximate the solution at 0.5. All right, so here's our analytic solution. All right, so it went through and it used the whatever method it uses to solve that. And then we're going to get the approximate at 0.5. So I'm going to say, let's just call it actual P5.5 is going to be equal to, when we substitute back into the analytic solution, and we're going to substitute 4x, and the new value is going to be 0.5. All right, and of course we're going to get like an exact solution, because if we just plug 0.5 in, it's going to be like the exp at 0.5 and all that stuff. So that doesn't really help us too much. So what we're going to do is we're going to do an fprintf, and we're going to say the analytic solution at x equals 0.5 is, and let's just do a %.6f and then a /n. All right, and again, make sure you use /n. Don't use \n, /n to go into the next line. And we're going to use actual P5. All right, so this should give us the analytic solution. This should be parts A and B really nicely put in here. All right, so that's pretty easy. We've done all this stuff before. Now, what we're really interested in is this ODE 45 function. All right, so now what we're going to do is we're going to open up a new file. So just click on the plus right here, or you could just go to open and you could just open something new, or you go to new and you do a new script. So either way you want to do it. And what we're going to do is we're going to type the little function of this particular ODE right here, this y prime. So I'm going to say function, and I'm going to call it, let's just call it f equals, I'll just say ODE fun1. And the parameters for that are going to be x and y, right? So for your computer science folks, that you're just building a function with two parameters right here, right? And the function that I'm building f is going to be equal to 2x minus 3y. All right. Now I'm going to save this, okay, as ODE fun.m. And once you save it, what you're going to notice is in the left column with the current folder, it's going to build yourself a function. All right. So that's important that it looks like this. If it doesn't look like this, then you're going to have to go back and you're going to have to try to build up your, maybe try a new file and start it over again. All right. So now I'm going to flip back to my untitled 19. Okay. And now I'm going to go ahead and solve analytically. All right. So I'm going to say x1, y1. All right. So input output, and I'll show you what this builds in a moment, is going to be equal to, we're going to use the ODE45 function. We're going to call the function ODE fun1. All right. So we're just basically saying, I want to read this in and put it into the ODE function. All right. I'm going to use the step size. All right. So right now, we're going to start at 0 because the initial condition was y at 0. We're going to go up to 0.5 and the step size is 0.05. All right. So we're going to say 0.05 colon 0.5. All right. And again, that's the initial value, the terminal value, what we're trying to approximate, and then the step size in between. All right. And then the initial condition was that y at 0 was equal to 2. So we're going to put a comma 2 there. All right. Now I'm just going to execute this, and this doesn't give us our solution yet, but it is going to run and it's going to give us a table of values. All right. So these are the x values. Okay. So basically we have our step sizes. So 0, 0.05, 0.1, 0.15, etc. And these are the approximate values of the function at each of those steps. The number that we really care about are the last numbers in each of these rows. So what we're saying is that when x is 0.5, then y is 0.0670. Okay, so that's the number we really need right here. All right, and what we're going to do is we're going to say that the approximate answer is going to be 0.6070. All right, now that's the value from the ODE. All right, so we're going to say fprintf, and we're going to say the approximate value from ODE 45 is 0.6070 /n. All right, and we can go ahead and run this. I'm going to suppress this, so make sure you suppress this so that way it doesn't always come out. And then the 0.6070 is the approx. So let's run this. And here we go. So now we have the analytic solution. We have the analytic solution at x equal 0.5, and we have the approximate value from ODE 45. And we could say when x is equal to 0.5, just to be a little more specific if we wanted to. All right, so that takes care of A, B, C. All right, we're going to compute the percent error. All right, so I'm going to call that P error. And that's going to be equal to the absolute value. Well, we don't even want the absolute value. We can take the approximate minus the actual P5 divided by actual P5 times 100. That's going to give us the percent error, right? And we're going to do an fprintf, and we're going to say the percent error between the analytic and approximate values is, and we could just say percent 0.6f /n. and we're going to say comma and P error. All right. And just to show you what all that looks like in one line, essentially we're just printing out this message. This is the approximation to 6 decimal places, and that's the percent error. So let's go ahead and run this. The percent error should be pretty small. The percent error is 0.007%. All right, so it's not 0.007 for the error, it's 0.007. All right, so notice that this is the exact, this is going to be the approximate. So they look pretty close to one another. One other way to determine how close these are to one another is the graphs. And so let's plot the code for the analytic solution to plot the graph from 0 to 0.5 as well as the ODE 45 solution. All right, so to do that, we're going to go to the next line. I'm going to do an easy plot of our actual P or our analytic solution. So analytic sol. And we're going to do that from 0, 0.5. We're going to turn a hold on because and then I'm sorry, and then we can go ahead, not X plot, but EZ plot, excuse me. And then I'm just going to title this one so that way we know which one's which. This is the graph of the actual solution. I'm going to turn a hold, or I'm going to use the word figure, and that's going to actually print out the graph. Then what I'm going to do is I'm going to go ahead and do a plot of x1 comma y1. All right, because these are the values. Remember, we got a table of this. So let's say x1 comma y1. And I'm just going to title the graph that this is the title or the graph of the ODE 45 solution. All right, so I'm going to run this. We're going to get 2 more graphs out of this, and then we can finally answer part G. All right, and we're just going to move this over. All right, so if you look at the 2 figures, so here's the graph of the actual, here's the graph of the ODE solution. They look almost identical. All right. If we had the range scaled the same way, notice that this goes at like 2, and this goes to 2, and then it comes all the way down here. All right, so if we were to plot, graph the points, we would probably see that they're really close to one another. All right, with respect to the grids. All right, we would just have to make the range the same. All right, so the good news is these graphs look the same. Also, the good news is that going back here, is that the ODE 45 as well as the analytic solution look pretty much the same. The percent error is small. So what we can say as a final part for this, we're going to fprintf, and we can say based on the similarities in the graph as well as the approximations for the solutions and the percent error, ODE 45 seems to provide a reasonable approximation to the solution of the D/N. All right, and that'll just print out. All right, so it's pretty long there, but no big deal. We'll just go ahead and run it. All right, and it just gives us this nice line that tells us that we can analyze the solution. So pretty cool that we can use MATLAB to be able to now get the approximate solutions of these differential equations, graph them, and kind of tie everything together with what we've done with respect to our differential equations and the ODE 45 function.